assumption is normality. We want to check whether the residuals are normally distributed, okay, if according to the variables. So very quick one, QQ normal quantile probability plot. Okay, they are used for that. Shapiro.test is used for that. Okay, and then we will now use another kind of application to test for the residuals. Now, this is an interesting area. Okay, one of the assumptions of regression is that the error term should be normally distributed with a zero mean. Do you remember that? That zero mean is what we are checking here. So let's go and do some checks of the normality assumption. So the normality assumption, we can use the quantile normal probability plot. That is a command I'm just going to run here. I've highlighted it and I'm going to run there. This is it. Okay. And you can see that, you know, if you look at it carefully, okay, forget about the observations 14 and 24, which kept showing. But you can see that it is telling you the deviation from the line, the fitted line, okay, which seem to show some bit of non-normality. Okay, again, graphs are just checking. Okay, and this was the original one, and this was the line, the quantile normal probability one. The next command will give you the test, because remember, the graphs are fine, but you need a test statistic. And we always use the Shapiro.test. So this is a Shapiro.test. We run that, and down here, it will tell you the p-value. And in this question, the p-value for the Shapiro.test is 0.002. 0.002, okay, which shows that, and normally, if the residuals are normal, okay, then the p-value is greater than alpha. When the p-values are greater than alpha, then the data is what? Normal. But in our case, our p-value is not greater than alpha. Our p-value is almost zero. So it appears to show that our residuals are not normally distributed. Okay? So keep that in mind. We'll correct this when we get to heteroscedasticity. Okay, our residuals aren't normally distributed. Can you live with that? Absolutely. You can live with that and still talk about your results. Okay, I'm just telling you those assumptions that you can ignore. Even if you check and there are some problems, you can ignore and still move along with your results. Now, there's another package that you can use to check this. And that package is a library olsrr. Okay, it will load the test, another residual normality test. Okay, you have to have this library installed. It's a package. These installations are one-time installations. So let me just show you. Okay, it is called library olsrr. Okay, that's a package that I'm going to install in R. And so you click on the install package and then install it in R. Now I have installed it already. Other than that, you go to packages here, install, a pop-up will come. And in that pop-up, you type olsrr. If you have a fast internet, you install it. I've installed it, so I'm not. And then you come to library olsrr and just load the package. And then do the next command. And that next command I want to show you here. Okay, this is the next command, ols_normality gene multi. That's what I decided to do. And this is interesting. Watch it, because it's going to tell us something interesting. Do you remember that the Shapiro.test appears to show that the data isn't that normally distributed? Do you remember? Now watch here. Let's go and run these results and then you see. Okay, if you run these results, look down there in the console, the p-value, Shapiro.test, that's what it gave us before, but it's added other ones. Okay, there are other tests. Kolmogorov's-Smirnov tests, it shows what? 0.07. So that one is about 7%. So it appears that that one is indicating that the data is normal. Kramer-Vontis-Misses is showing that it's not normal. Anderson-Darling is showing that it's not normal, looking at the p-value. Okay, when the p-value is less than 5% for normality, it's not normal. So again, 3 tests are showing that it's not normal. 1 test is showing that it's normal. And so it appears that our data residuals is not that normally distributed. Okay, so once again, when we get to the heteroscedasticity, we'll use it to handle the situation. But the key point about normality is it. Normality of residual is only required for valid hypothesis testing. In other words, the normality assumption assures that the p-values of the t-test, the f-test will be valid. Regression merely requires that the residuals are independently and identically distributed. That's what regression is requiring. Okay. So again, this is an indication we don't have to bother ourselves so much to force it to be normally distributed. Okay. But if it is, it's nice. We can use kernel density, quantile normal probability plots to check for normality of the residuals all the time. So this is just to let you know the situation. All right. So it is very important to handle all of the outliers, small data sets. All of these things can lead to non-normality. Outliers can bring about non-normality. Small, when you're having small data, and we have small data, okay, just 40 observations, okay, so that can lead to misspecified errors and non-linearity, and in this case, residual assumption violations. And like I've already told, we can handle all of this when we get to heteroscedasticity, okay, using something we call heteroscedastic corrected covariance matrix, or bootstrapping, we can use that, or trimming, we can use our windsoring, we can use that robust regression. I've shown you that. Data transformation, we'll look at that later on, non-parametric statistical testing, nonlinear models, all of these, they go bigger, but I don't want us to bore ourselves with all of this. Okay. All right, there's one last thing I want you to note here, which is interesting. It's just a beautiful package in R, which you can just give that command and it will tell you all of the assumptions. Okay, not all, but most of the assumptions easily without struggling. It is a package known as gvlma. gvlma. This assumption, once you install this package, gvlma, okay, and then run your command, it will give you the complete model, and then it will also tell you about the other kind of assumptions, whether they are passed the test or they didn't pass the test. Okay. Let me just go and do that and show you finally before we wrap up this section. So the package is called gvlma. So once again, you always go to package, you go to install, okay, you type gvlm, and then it will pop out by itself. You can install it, and then you can library it into the command window. And once you do that, you can now give the command using the name GV model, and then gvlma, gmulti, which is the name of our data. I just called it GV model, and then summarize the model, and you get this result. It's a beautiful thing. Watch it. Watch it. It's a beautiful thing. Very beautiful. Because here, it will run the entire regression, as you can see here. To run the entire regression, give you the residuals. It will tell you the coefficients and whether they are significant or they are not. Everything that we've been doing, it will tell you. This is the original model that we had. It will tell you everything. It will tell you the significant, the R square, the p-value, the adjusted R square, and all of that. And the most critical point is here. It will tell you assessment of the linear model assumptions. So it's checking whether the linear model assumptions are properly handled using the global test on 4 degrees of freedom. Okay. And the level of significance is 95%, 0.05% significant. So it tells you first, it checks the global. Okay, so I was saying that it gives you the assumption test. So you can see the skewness, it tells you the assumption acceptable. Ketosis assumption is acceptable. Link function, that is the linearity assumption. You see, telling you that it's not that satisfied. Heteroscedasticity assumption It's not as, it's acceptable. Okay, so it tells you, this one gives you a bit of a feel. So just find some information about this and read it so that you can interpret those results. How do you find information? Just type in your search here, gvlm, and then it will pop out. Once it pops out, you can click on it and you'll find what is doing there. Okay, you can read a bit about it, interpretations about it, and all of that. Okay. And this is to just tell you what is really, what it really is about, and you can feel it and then appreciate it. Okay, I thought that was interesting because I've never known this until just last week, and I said, oh no, let me give it to you guys. Okay, so whenever you're doing assumptions testing, you can check it. All right.